it's about time to start. Maybe some more audience are coming since it's time. This morning's lecturer is Natalia Chepiga, and as you can see, she's telling us about matrix product state.
Thanks a lot, and I would like to thank for your kind invitation. It's my first time at the SSP. So I was asked to give rather introductory lecture on DMRG, so the first part would be really pedagogical, and I try to explain all details that if you're about to implement something based on MPS or Tensor Networks, I hope it's going to help you to start. And then I'll discuss three different applications, different from a matrix product state point of view. And basically that's the plan for today. I start with DMRG as I told, and then I'll discuss rather old project on spin-one chain. It's more or less kind of classical implementation of DMRG, but with some non-usual extension to target excitation spectrum. Then I'll discuss a recent a project with Steve White on Tensor Networks. It's an extension of DMRG beyond one-dimensional setup. And on the lecture next week, I'll discuss DMRG for a hard boson model of Rydberg atoms. So it's going to be more about implementing symmetries and local constraint into DMRG, and also physical results that we can get with such an approach. So let's start. And the first question is actually why all this Tensor Network stuff works. And the answer is given by the area law. Without going into much details, let me briefly overview what it tells us. So in many body physics, what we try to do is to solve the Hamiltonian of many particles, and the main problem that we face is the Hilbert space grows exponentially fast with the number of particles. So exact diagonalization can deal with the systems up to 30-40 size, depending on the model, but beyond that, we need a more advanced and approximate technique. We heard a lot of talks yesterday about Monte Carlo, but we know it suffers from a sign problem, and second method of choice, especially in 1D, is DMRG, Tensor Networks. So the idea behind is the following. The observation is that the random state of a Hilbert space has an entanglement that grows actually that is much more entangled than a low energy state of a local Hamiltonian. And that's what we're actually usually interested in. We are interested in a local Hamiltonians, want to find a ground state or low energy state of this Hamiltonian. So we do not want to target a random state of a Hilbert space, but what we want is actually a small corner of such Hilbert space. And therefore, it would be nice to find a way to diagonalize our Hamiltonian, not in an entire basis, which at some point we cannot write as soon as we include many particles, but try to diagonalize it directly in this small corner of the Hilbert space. And in more mathematical way, it's formulated with the area law. So in random state of a Hilbert space, the entanglement scales with a subsystem. So imagine we have a bus of a system, and we try to bipartite it into small subsystem A, or not necessarily small, and its environment B. So the entanglement between the subsystem and what's around scales as a volume law, scales as a number of particles inside the subsystem for a random state. But for a ground state of a local Hamiltonian, the entanglement between the subsystem and the rest scales only as a surface, as a number of particles on the boundary area between these two subsystems. So for 3D space, it means the surface, it means the area, but for 2D system, it means just a perimeter, the number of particles sitting on the line that separates subsystem and environment. And for 1D, it actually means two domain walls. It means just a constant.
Question.
Yeah.
What should the random state after volume law? Or random state?
Well, it's the most generic case. I would say there exists a random, there exists some states that does not satisfy it, but let's say it's upper value, right? It's the most what we can have. Okay, but what does it mean in practice? it means that the number of states that are relevant to describe our low energy state actually scale as exponent of log, and you see it's a constant for 1D. That's why we can approximate it with a finite bond dimension using our MPS. So the goal of the whole MPS algorithm, or DMRG algorithm, would be to try to work directly into this corner of the Hilbert space. Now about graphical notations. Again, since yesterday you are probably familiar a lot with this, but let me just mention them for completeness. So as soon as I write a bulb, I mean there is a tensor. And then depending on how many legs sticking out of this tensor, it would mean a rank of the tensor. So if I have no legs, it would mean a C number, complex number in general. If I have one leg, it's a tensor of rank 1, so it's a vector. 2 legs mean a matrix, 3 legs means a three-dimensional tensor, and the simplest tensor, the building block we will use in DMRG, in matrix product state, would be this kind of rank 3 tensors. Rank 4 tensors also can be met in DMRG. It would be a matrix product operator, for example. And in IPEP, the building block would be rank 5 tensor, and one can continue whenever limited. You can go to infinite dimensional tensors as well. So graphical notation continues. Whenever I have two bonds that connect two tensors, I mathematically sum over repeating indices. Here it is. And the results of this summation is going to be yet another tensors of rank that equal to a rank of non-connected legs. So here I multiply a rank 3 tensor with rank 4 tensor over 2 legs and end up with the rank 3 tensor here, because here it was 3 empty legs. In practice, we never do the summation directly, like step by step, but what we rather do is to reshape these tensors into a matrix form and then use an optimized routine to multiply them. The complexity of such construction is given by a product of the dimension of all legs that involve in this contraction. So you count the dimension of all open legs and you count the dimension of all connected legs, avoiding double counting. And it implies that in 1D, the order of contraction matters and matters a lot. So for example, if I try to contract this type of tensor network, for example, in this way, you can easily realize that this big matrix, actually the number of legs sticking out of it grows. It means the complexity grows exponentially as soon as I try to increase the number of absorbed tensors, and it's bad. It's not what we want. If we, for example, try to do it another way, like this, it's easy to notice that the number of legs sticking out of this big tensor always bounded by 4. So my complexity stays finite. Yet another important mathematical tool that we use in DMRG is singular value decomposition. And in linear algebra, it basically tells us that for any square matrix could be decomposed into 3 matrices with the following properties. U and V matrices are unitary and multiply with its conjugate to 1, to identity. And the middle matrix is a matrix of singular values, a diagonal matrix with non-zero entries. But if we try to now imagine some state, quantum state, a real quantum state of local Hamiltonian, we can write it as a product, the coefficients, we have d to the n different coefficients, but we can bipartite the basis into subsystem A and B and write this coefficient as a matrix. But then as soon as we have a rectangular matrix, we can SVD decompose it into U, S, and V matrices. And now there is no approximation yet as soon as we sum over all possible K indices. But what area law tells us that it's not actually necessary to do so, we can approximate efficiently the state by summing over some bounded D indices, which is smaller than the entire Hilbert space of our system. If you try to implement DMRG, or if you're new to the field and want to know more, it's always useful to start to play with simple wave functions. So what one can do is, for example, to get a wave function from some simple code like exact diagonalization for a small system and try to rewrite it with a tensor network with matrix product state. The way to do it is the following. You start with a ground state that you obtain for some other technique, and you think about it as a tensor with n legs, n is the number of your particles, and dimension of each legs would be equal to a dimension of your local Hilbert space. And you reshape it into a matrix with a dimension d by d in n minus 1, and then you SVD decompose it, and you take U matrix as your first entry of the matrix product state. And you multiply back the S and V dagger to the second matrix. Now what you do with the second matrix, you again reshape it. You have this D index here, you add yet another D on top, so you have matrix D squared by D n minus 2. And what you do again, you SVD it, and you again absorb, take U matrix here as a tensor for the second side, and SV matrix here, and you continue doing so like this. So if you don't do any approximation, the bond dimension would increase as soon as you move away from the boundary. It would increase exponentially. But what area law tells us is actually we can bound it to some constant value, so it would actually increase for some sites and then remains continuous if we are talking about gap system and ground state.
I have a question.
Yes?
Suppose your wave function that you had translation invariance. Mm-hmm. Is there a procedure to decompose it so that all these tensors are the same? I mean, so the procedure
starting from the wave function.
Yeah, so I know the wave function, if I translate it by 1 unit, it comes back to itself. So it has full translation lines. So you might think that there might be some procedure to write it as a tensor product like
but
this.
You have boundaries.
What's that?
You have boundaries.
Yes.
No, but I'm imagining another problem which doesn't have boundaries. And I mean, it also has...
There is a way to find it directly in translation invariant state, but to start with some state and decompose, I mean, not immediately. Well, yes, but the question is if you start with if you already have your wave function.
Yeah, I mean, to minimize the overlap for translation of MPS with scaling chart. What's possible?
Okay, yet another comment here. So as you notice, I start from the left and move to the right, but obviously you can start from the right, move to the left, and this procedure would create a left normalized matrix, the other one would create a right normalized matrix built out of this V-dagger tensors. But obviously what we use in practice is a mixed canonical form where we combine both left and right normalized matrices and a vector of Schmidt values that connect this left and right normalization. Normalization condition in a pictorial way takes basically the following form. So when we connect our matrices through left normalized matrices through a left and physical bond, we end up with identity matrix, and the same for right normalized matrices. And that's going to be very handy to simplify the calculation, for example, of observables, but also to find variationally the ground state wave function, because what we want to do is to find actually the ground state that minimizes the energy, and basically we want to solve this equation. Psi h psi over psi gives a minimal of the energy, and then psi is normalized and it's reduced to this simple expression. But when we do variational optimization, it actually turns out that instead of solving a generalized eigenvalue problem where some effective Hamiltonian is needed to diagonalize with respect to some effective normalization matrix, we only end up with a simpler standard eigenvalue problem that is easier and more stable to solve. Before we move actually to the DMRG algorithm itself, what we're still missing is how to rewrite the total Hamiltonian into a local product of operators, because if we cannot do so, we cannot gain anything. We still need to write the full matrix. So we need to find a way to decompose the Hamiltonian also into kind of local products of operators. And that's the notion of matrix product operator. So I'll try to explain it, how one can construct the MPO, one of the possible ways to construct MPO for transverse field Ising model, and then it will be a small exercise on construction for a bit more advanced models. So first of all, we try to write down all terms of the Hamiltonian, including the direct product with identity operators, that has different entries on a selected site J. So, for example, in this transverse field Ising model, for example, I have a term that has entry Hj, the field term, and then on the left and on the right of this side, I have identity matrices. From this term, I have two contributions. So either I have GSJ minus 1 and Sj entry, or I can have GSJ and J plus 1 entry. And this would create like two different entries on my left and right parts. But then I can have also an entire term on the left, either this one or that one, or the entire term on the right. From implementation point of view, as soon as interaction is completed, as soon as the whole term is located on the left or on the right, it doesn't really matter. So we can just say, okay, we have like full term or complete interaction included there. So for basis, it doesn't matter. And what we end up is 5 different entries, which means that our MPO resultant MPO would have 5 different non-trivial entries in the matrix. But it's not the dimension of the MPO. The dimension we count by different states. So here you see we have 3 different entries of the basis on the left and 3 different entries of the basis on the right. So our MPO is going to be 3 by 3 matrix with 5 non-trivial entries. And we simply try to fill based on this basis, we try to fill the entries from the term we had before. So now an exercise, try to construct the Hamiltonian for either nearest neighbor Heisenberg model, or if you're familiar with this, and for nearest and next nearest neighbor Heisenberg model, or if you're advanced DMRG user, you can try to construct MPO for this model with 3-site interaction, and the competition would be to have the smallest bond dimension possible. So let's say 2 minutes for you to try. I'll give correct answer. I'm not asking to you to give an answer, but just to play a bit.
I'm sorry, I'm not sure what the exercise is.
Sorry?
What is the exercise?
We try to. So this was a matrix product operator for Ising, for transverse field Ising.
Oh, I see.
Now I changed. You see?
So you want us to have the same table?
Yes. Yes. Yes, but for Arthur Hamiltonian. Yes. Who's ready for the first one? Okay. So the answer is the following. We don't have on-site terms, so the left corner remains empty. We have identity on the first and last entry of diagonal. And then, well, you can mix them up. Doesn't really matter the order, but be sure that if you have S plus, S minus on the left, you would have opposite S minus, S plus on the vertical. So they multiply, when you try to multiply two matrices to each other, they take a correct entry. So who's done G1, G2? Do you need more time? Tell if you need more time, otherwise I go to an answer. Okay. So this is an answer for G1, G2. That's very similar to G1, the one we saw before. But then on top of it, we have a next nearest neighbor interaction, so bond dimension of MPO increases. And obviously, if we have term Sj, I, j plus 1, Sj plus 2, we need to add identity matrices that would multiply on these two before we move in to the last vertical. And who's trying G1, G2, G3? Any success? Okay, so if you try to do it in a straightforward way, you get a bond dimension which is quite high, and the idea actually to play a bit with the physics, and one can show that it actually reduces to bond dimensions that you have with G1, G2. So you define something that's equivalent to a quadrupolar operator. You see pure physics, no mathematics at all at this point, and then you can plug it into the operator of G1, G2 model without additional computational cost here. Okay, let's move further to DMRG. It was a short warm-up for you. So what we try to do is to keep all tensors but 2 or 3, depending on the routine you use, or 1, and optimize them variationally. So we take our matrix product operator that we just created, sandwich it with some guess wave function written in terms of MPS, and then what we do is to treat this rank 8 tensor as a matrix. So we group the legs on top and the legs on bottom. We have a square matrix, and then we diagonalize it. And the result of this diagonalization, the eigenvector, is decomposed into, using SVD, into left and right normalized matrix, and then we plug it in, let's say left one, into this original part, and we increase the environment on the left by one side, and at the same time we remove one tensors on the right. So what we've done at this step is one simple DMRG iteration, increasing, let's say, right move for the environment. And now, again, we treat it as a matrix. We diagonalize it, we do SVD, and we take the left normalized tensors back, absorb it to the left environment, and at the same time we remove tensor on the right, diagonalize the matrix. This would be like a matrix of effective Hamiltonian. A Hamiltonian written in the kind of truncated basis of defined by your matrix product state. Again, we diagonalize, and as soon as we hit a boundary, we start to move into the opposite direction. So now we absorb a right normalized tensor to the right environment and start to make a left move, and continue until the convergence is reached. So moving entirely from a left boundary to the right and from right to left would correspond to a full DMRG sweep, and during the sweep, each tensor is updated twice. So now the question, how we actually came with this initial guess, with the original guess with which I started, and there are 3 main ways of doing it. Either start with a product state, which is matrix product state with a bond dimension 1, or start with some finite bond dimension but defined by some random matrices, random states, or doing infinite size DMRG, which is, however, not always possible, but when it is possible, for example, for translational invariant Hamiltonian, it gives an extremely good wave function. And then it takes just a few sweeps to converge. So, infinite size DMRG, how does it work? We start with the first or few or 1 tensors that could be essentially an identity matrices, since the bond dimension is still quite low. And then we contract it with a matrix product operator on the first and last sides to create an environment. Then we insert a matrix product operator in between for two sides, and again we treat it as a matrix, diagonalize it, make SVD, and absorb both vectors at this time to the left and right environment. So what we've done, we increase the number of sites in our system by 2, and now we again insert 2 more sites, diagonalize, make SVD, and continue until the desired size of the system is reached. Just a few comments about implementation of symmetry. Much more is going to be next week. Today is just the idea. So if we want to implement conserving symmetry such as particle conservation number or total magnetization conserved in the Hamiltonian, we assign a quantum number, quantum labels to all physical bonds here. Why doesn't it work? And see how it flows, see how they merge into auxiliary bonds. So this, and then if we impose some condition on the total quantum number in the system, for example, total number of particles, when we diagonalize an effective Hamiltonian, we try to get this correct number by the entries from the left and from the right. So why it is important? Because if the symmetry is conserved and you profit from it, then you can write your tensors in a block diagonal form. And many operations can be done directly inside the block and not with the entire tensors. So again, a small example. For example, spin 1/2 chain, I start with the first left matrix. Obviously, it has the labels 1/2 minus 1/2, and the labels of auxiliary space remains basically the same. And you see it obviously has block diagonal structure. But then if I try to do the same with second matrix, now I have some magnetization that comes from the left. I have magnetization that comes from my physical bond. I merge them, I superimpose them, and if I sort it in a way, the total magnetization scale, I have a block diagonal structure, and it persists even for further matrix. And even when you start to truncate, you truncate within each block separately, so you don't need to do an SVD operation, an entire tensor, but just on a block, each block separately, which reduces computational cost a lot, but also reduce the number of states you target and allow to fast conversion. Okay, and the last thing I want to mention about implementation is computing observables. Again, it's just an example of a few observables, but I hope it's going to give you an idea for your future needs. So let's start with the simplest one, is the nearest neighbor correlation. What we want to do is to compute an expectation value of this operator with our ground state, which is written in the matrix product form, and to profit from the normalization condition, we want to use it in a mixed canonical form. So remember, we can then try to eliminate the one which is ends up to identity matrix. But this tensor network is wrong. So what's wrong with it? Any idea? Something is missing.
The gauge?
Hmm?
The gauge?
No, Schmidt values. And that's essential. Why it is essential? Because the matrix product state itself doesn't carry information about ground state. It's just a transformation of the basis. The basis is convenient to approximate the ground state. All information about your ground state is actually contained in this small vector of Schmidt values. Therefore, it's essential to include it. Okay, but now we can play. We can eliminate what we want to eliminate from the beginning. So this is just identity matrix, which I reduce, and we end up with such a simple expression. And in the contrast to standard DMRG, not an MPS-based DMRG, but original one, to compute observables, it's a big profit. If you need to compute the local observables, we need a local number of tensor. We just do it locally, and it simplified life a lot. If we have on-site measure, doesn't really matter which one you choose, either left normalized, right normalized, but be sure to include singular values in your tensor network. And also for long-range correlation, again, as soon as you eliminate everything which you don't like, then it doesn't really matter where you end up having left normalized and right normalized tensors, but be sure to include to include singular values in your contraction. Okay. Any question about DMRG for now? Like immediate question.
Are you going to talk about abelian symmetries?
Not really abelian symmetry. I'm going to talk about local constraint, hard constraints, which is similar to symmetries next week. It's going to be an entire 1 hour talk on this.
But non-abelian symmetries, like spin and charge?
No. Okay. So now let me move to the first application. And this is a rather old project done in collaboration with Frederick Mila from EPFL and Ian Affleck from UBC, where we apply this algorithm to kind of conventional spin chain models, studying critical properties of the system. So coming back to physics, spin chains, Heisenberg spin chains, we know spin half integer is critical. Spin one chain or integer chain can be characterized by a finite Haldane gap. In particular, spin one chain is also characterized by an emergent spin one half H states that on a finite system couple through an entire chain to form a singlet or triplet with exponentially vanishing energy splitting, also known by Kennedy triplet. But the question is, it has a bulk gap, but can we drive it also into a critical regime? And one of the most famous textbook examples is a nearest neighbor interaction complemented by a biquadratic interaction. So when this biquadratic interaction is positive, we end up in a critical quadrupolar phase here. And when it is negative, the transition to the gap to dimerase phase is continuous, which means that also we have critical point. It is exactly solvable by Bethe ansatz, and it is Tahtajan-Babujan point in Wesu-Minowitten SU2 level 2 critical universality class. What is distinct for these two transitions is the both magnetic, namely singlet triplet gap, closes at this transition. And in the following, I'll show that there is actually another possibility of a non-magnetic transition that occurs entirely in a singlet sector. So we're going to study this model, the one you've seen before, trying to create a matrix product operator yesterday in yesterday's talk. So it contains a nearest neighbor, next nearest neighbor interaction, and a three-side interaction. These two terms alongside with the biquadratic interaction appears as next to leading order expansion of a Hilbert model. So they play essentially the same role, although it looks more complicated, of course. If you look at this term separately, it's easy to realize that the energy of this term is minimized when the spin-spin interaction is large and of opposite sign on two nearest bonds. And therefore it's distinct, it favors a dimerased phase. So we expect, for lattice 3, we expect a dimerased phase to emerge. When spin 1 is actually reduced to spin 1/2, the model is reduced to a G1, G2 model studied by Majumdar Ghosh, so it's a natural generalization of this model to larger spins. So to give you a motivation why we actually studied, why we looked at this modeling originally, let me briefly review what has been known before we start to address it. So in the absence of G3 interaction, so simply G1, G2 model and spin 1 chain, back in '96, Scholwerk and collaborators showed the transition between Haldane phase to the next nearest neighbor Haldane phase is topological and is the first order. There is no intermediate phases on the way. On another line, as expected, we indeed observe a dimerased phase. There is no intermediate phase in transition between this Haldane phase to dimerased phase is very similar to the one observed in bilinear biquadratic chain, similar to Tahtajan-Babujan point. It's Wesu-Minowitten SU2 level 2, a continuous transition here, but there is also a very special point on this line, which is located at 1,6. This point as a ground state is given by an exactly explicitly dimerized state, so it's known exactly, and later it has been generalized to an entire line along which this exact state remains an eigenstate. Well, not necessarily ground state, but obviously it stops being ground state at some point, and then it means that dimerization drops abruptly. And then it means that we hit the first order transition, but then it's not compatible to the continuous transition observed here. So the idea was to try to accommodate it into a phase diagram and try to find what's going on numerically with DMRG. And that's the answer. So what happens, the transition indeed starts as a continuous and remains so for quite a while, but then it turns into a first order transition via a very unusual endpoint, which is in the same universality class as the entire continuous line below it. It happens due to the presence of marginal operator in the theory that changes sign from a negative to a positive. So when it is negative, it's renormalized to zero and leads to a critical Weismann-Witten theory with some log corrections. And when it's positive, it becomes important, so it doesn't lead to a continuous transition, but instead it goes to a gapped or first order transition. The transition between next nearest neighbor and Haldane phase and Haldane phase always topological and always first order, at least within this parameter range. And the transition between next nearest neighbor Haldane phase and a dimerized is also continuous, but it's in an Ising universality class, which is non-magnetic. So there is a nice field theory behind it, which I'm not going to discuss into details, but what I want to mention here is why it's actually possible, why Ising transition can appear in such system. So this Weismann-Witten theory with a central charge 3½ could actually be decomposed using Cauchy relation into a boson and an Ising field. Boson field, we know, has a central charge 1, Ising has central charge 1/2, so they add up with indeed 3½. And what happens is, in the vicinity of this endpoint, the transition necessary occurs simultaneously in both sectors. But far away from this point, it's not necessarily the case. Two lines could split, and that's why we can actually observe an Ising critical line separately.
Question.
Yes.
The endpoint should have a supersymmetry.
Hmm?
The endpoint is the critical line. It should have a supersymmetry.
Why supersymmetry?
Because here you have boson and fermion. And also the central part is the 3½.
It's not feminine, it's Ising, it is Ising field.
There is a possibility to have a supersymmetry at this point, in particular from the conformal field theory for the central charge 3½ you can have supersymmetry.
Well, we didn't really study it, but okay. Nice to know.
What would be the consequence of that for the field matter?
I don't, at the moment I don't know, but I think there should be a supersymmetry at this critical point. This is a tri-critical point.
No, it's
instead
not.
Of, because it's a.
But that's the point, it's not tri-critical point.
No, it's a second order end point and first order end point.
Yes.
They meet at the same time. This is sometimes people call it a tri-critical
Yes,
point.
indeed, but it's not the case here. This endpoint occurs because of marginal operator and not because theory change. So it's not like an Ising critical line that ends at a tri-critical point. It's very different. It's rather like critical theories that we have in spin 1/2, and then we have a Kosterlitz-Zaulis transition. So it's the same idea. In the spin 1/2 critical chain, we have a marginal operator which is non-zero, and it changes its sign at the Kosterlitz-Zaulis transition, and that's exactly what we observe here. We have marginal operator that simply changes sign at this point. It's not tri-critical point.
Thank you.
And yeah, common isers, this one is not tri-critical. Because again, it's not ends. It just hits the first order transition.
You mean the middle?
Yes, it's a
middle point.
triple point. It's also remained Ising always through till it finally hits the first order. It's very unusual, but it's indeed like this. We checked it very carefully. So there are no tri-critical points in this phase diagram.
So you got this this transition, this two transition line from DMRG calculation, right?
Yes, but also from conformal field theory.
Can you remind us that exactly solved line? How does it meet these lines? There was a line where the model.
Yeah, okay. So it starts a bit away. It starts from here, and then it basically hits the transition here. So indeed, it hits the first order transition as expected.
So at that first order transition, the dimerized state ceases to be the ground state.
Yes. Yes. Well, just away from it. Yes. Okay. So how we probe actually this phase diagram with DMRG? Why DMRG is useful for this particular problems? First, we define an order parameter, and in this case, since we study dimerized phase, we define a dimerization. And here, what I plot is just the finite size results for a dimerization calculated in the middle of a chain with 150 sites, not very long system. And you can immediately see a drastic difference for different transitions. So first of all, you can distinguish continuous transition from a first order transition that has a pronounced jump in the order parameter. But in principle, you can also guess that a critical exponent is much smaller here than here. Okay, it's not qualitative idea, but it already gives you something. Now let's try to make it a bit more quantitative, and let's first look at the Ising transition, which is more surprising in this phase diagram. So what I plot here is a finite size scaling of the dimerization parameter computed inside the finite size chain in the middle for different points around possible phase transition. So when it goes down, it means that we are in the non-dimerized phase. When it goes to some finite value, we have a finite dimerization, so we're in a dimerized phase, and therefore we associate a transition with a separatrix that separates these two regimes. The slope of this scaling function gives us a critical exponent, and the value of the critical exponent agrees pretty well with a CFT prediction for an Ising critical point. Now, the second way of looking at dimerization is not as a function of system size in the middle of the chain, but then for a fixed size along the chain. So how dimerization scales away from the boundary. And what we notice that open edges favors dimerized state. It favors state, and therefore it fixes the boundary condition. And we know as soon as we fix boundary condition in critical chain, we induce Friedel oscillations that decay algebraically away from the boundary. And CFT has an explicit prediction of how the envelope should look like. So it's here. And the exponent remains the same, since the operator is the same. And again, what we observe is in a good agreement with CFT prediction 1.8. Okay, so you see already ground state calculation can give rather nice results, but, well, obvious drawbacks that we need to go to a fairly large system to get it. What we want to do is to probe this critical theory somehow in a different way to basically to confirm this Ising transition, to have an alternative way of looking at this criticality. And one of the best methods I can imagine is to compute a conformal towers that acts usually as a fingerprint of critical theory. Because playing with the boundary condition, we can change the boundary conformal field theory, and we can probe different primary fields of the theory. And since here we're talking about Ising critical theory, it is described by a minimal model of CFT. And minimal model means that we have a finite number of these primary fields. So if we're lucky enough, we can probe all of them in principle. Well, okay, so how do we extract actually this conformal tower? Conformal tower is a special structure of excited state of a spectrum. Before I actually move to our method, let me briefly review what has been done before. It's a conformal tower extracted from entanglement spectra, something that we naturally get when we do DMRG. So basically, it has no additional computational cost to look at this, but unfortunately, it doesn't work always. So in this particular case, Andreas looked at the open and periodic boundary condition, and the problem is that in boundary conformal field theory, this type of boundary condition requires many primary fields at the same time, so we have a massive degeneracy and we have many different excited levels on top. And in open boundary conditions, this method would not actually work because on top of true levels, we will have some fake levels that has nothing to do with the critical theory but appears because of open boundary in entanglement. But anyway, it's good to know that this method exists, and it's probably the easiest way to try it before moving to something more advanced. What we have done is actually to look at the original idea of conformal tower, at conformal towers built out of energy spectrum. But the question is, how do we compute an energy excitation spectrum with DMRG? And the task is not at all trivial. Well, in the lucky cases, when we know that the excitation is, can be distinguished from the ground state by some quantum number, we can run our DMRG again in different symmetry sector, and then we get a ground state in this symmetry sector and compare the energy of the two and get a gap. But it's not the case in Ising transition, and well, it's not the case if you need several states within one symmetry sector. And then what conventional DMRG suggests is to use a mixed state. So instead of taking a ground state when you diagonalize your effective Hamiltonian, you take several states, you add some weights to them, you mix them, and you plug it into your left to right environment. This either means that the ground state is spoiled because you add the wrong state with some non-zero weight to it, or if you want to keep it as same accuracy as before, you need to increase the bond dimension to accommodate this another excited state basis inside. Matrix product states allow actually a better option to construct the lowest energy state that would be orthogonal to all previously constructed states. It means that the algorithm has to be rerun for every excited state that you might be interested in, and it also means accumulation of the error. So if some of the state has problem to converge and you converge it not very well, then make an orthogonalization to a badly converged state, you accumulate this error again. But it's rather systematic and trustful way, I would say. So it's going to be handy in principle. And there is yet another method proposed recently in Frank Verstraete group. Frank Verstraete group. I'm not sure whether Laurent is going to talk about it, but probably yes. So there are two more methods. Either to use translationally invariant MPS with a periodic boundary condition and replace one tensor that you then move around this MPS, and you can get excitation as a function of momenta. But here, remember, we don't want to have periodic boundary condition. We want to have boundary, and we want to play with boundary. Or play with a quantum number on an infinite system by creating a domain wall that would not fit directly, so that would create a excitation just because it's a quantum number mismatch. And again, since it works on an infinite system, it's not really what we want. We want to see the boundary. So, in principle, this third option remains a matter of choice. However, what we notice that sometimes it is not actually necessary to rerun the simulation. Sometimes there is a simpler option. One can target many states using diagonalizing the effective Hamiltonian and simply keep track of the energy as a function of iterations. So why does it work? If we again come back to this picture, what happens is we have a total Hamiltonian, our entire Hamiltonian as we would have in exact diagonalization, which we sandwich with matrix product states that basically rotate and truncate the entire basis into some smaller Hilbert space that meets our need. But could it be that this truncated basis is actually good not only for ground state, but also for excited states? I don't say that it's always true, but there are many situations where it is true, and it turns out that there is a situation we are interested in. So there is a trivial example, actually, when it is true, is when the system size is not too big, so the bond dimension can be still exact, and therefore our DMRG is basically an exact diagonalization. You have a question?
So can I ask a question? So you only calculate the ground state, but you calculate all the such state or effect.
Yes, so what I do, I treat it again as a matrix, as before. I diagonalize it, but I diagonalize it for several states, not only for ground state. But when I absorb only the ground state. That's the main difference from conventional DMRG. So my ground state remains unspoiled, my method remains variational, but I can see the excitation energy.
So the difference from previous DMRG calculation, targeting multiple states, is that we only use the ground state to do the transition.
Yes, yes, indeed, yes. Also this conventional DMRG is designed, this mixed state DMRG was designed for gapped systems. And in principle, it cannot work there. I mean, it works, but not very well. Well, you will see. So, okay, this is a trivial example where my size is small enough so I can keep all states, and my matrix product state variational optimization basically reduced to exact diagonalization. And you see in the middle of the chain, I basically reproduce my results obtained with exact diagonalizations shown with gray lines, and colored would be a DMRG calculation. And also I here show arrow between exact and DMRG. So in the middle, indeed, it reproduces perfectly the spectrum. And close to the boundary, it's not expected to work because due to construction, the bond dimension decreased towards the boundary. So the basis is no longer full. So again, we try to compute excitation spectrum in an approximated way, and we do not succeed, obviously. But this basically proves that, okay, in trivial case it works, but then where else could we expect it to work? And yet another trivial example is when we have a gapped state with a fairly small correlation length, and we have a localized impurity, for example, a weak bond in our Hamiltonian, and then diagonalizing the effective Hamiltonian around this impurity, we obviously will get the correct excitation spectrum, just because the left and right parts of the ground state, the tensors remain the same, because it's essentially gives the it's the same for both the ground state and excited states. The second example where it surprisingly works, and it works nearly with machine precision, is when we try to get an energy splitting between in-gap states. So imagine we have a Haldane chain with H states, and we know that H states are coupled to form a triplet or singlet with exponentially smaller gap. But it turns out that the state itself, the matrix product state, doesn't distinguish really whether we have spin up or spin down. It carries both of them until we actually diagonalize it. So we get it for free, and if you look here for, this is energy as a function of iteration for Haldane chain with 100 and 101 sites. We know that in this case we have a spin singlet, and in this case we have a spin triplet, ground state, and other way around for excited state. And so here we can actually benchmark the method by looking at the several states in a singlet sector. You see here is a ground state, well converged one, and here I have excited state. This is close to boundary where basis is too small, but in the middle of the chain I have very flat energy as a function of iteration, and I can compare it with the ground state energy in the sector of triplet, and you see a perfect agreement, basically machine precision, and an energy gap of the order of 10⁻8 can be captured with this method. But of course, the true usefulness of this algorithm, when we cannot actually distinguish this ground state and triplet by excitation, when, for example, a ground state is a triplet. And if we want to compute the first excited state, we need to target second state in the singlet sector, and it is the zero sector. And that's what we see here. And again, we have a flat event, which means that we have a truthful, faithful excitation here as well. But the main point where this idea works is in the critical system. So remember the area law that tells that on top of exponential decay of the Schmidt values, for critical system we have some corrections. We have log corrections that increase the tell is that it increases the weight of the Schmidt values, and therefore it increases the weight of the basis vectors that you keep in the matrix product state. It means that our effective basis is much higher, and therefore it could be much more suitable to many states rather than to just a ground state. So we benchmark this idea onto, well, transverse field Ising model as usual, because first it's critical, and second it's solved by Jordan-Wigner transformation. And here are the results. So gray line are results of Jordan-Wigner transformation. Here I show DMRG results for 30 states obtained within a single run DMRG. So basically, we get it for free. Ground state is here, and then many excited states. You see, we have problems close to the edges expected because the basis is too small. But then in the middle of the chains, we have a flat part, and as soon as the convergence is reached, the bands become flatter and flatter. So we basically can see and estimate how good our convergence is by looking at the energy as a function of iterations.
Does it also recommend generosity?
Yes. Yes, it does. So here, for example, you see 3 levels, and indeed it's a yeah.
So the iteration number here is not a whole sweep step, it's just every.
So here it's one sweep,
Okay.
and here it's another sweep, and here it's yet another sweep. Sometimes you need more, sometimes you need less, depends. But, okay, let's now compare this spectacular critical theory with what we have in the gap. And you see we have a total mess. It doesn't work at all. So, and as expected, we have a finite number of vectors. We try to approximate a state which is not supposed to be in this basis. So it is kind of natural that we see it here. But then if we come back to a critical state, the results are really remarkable. You see that even like finite size splitting of the order of 10⁻⁵, we still can capture it. And imagine it's at no additional computational cost. You still, basically you run the algorithm for the ground state. Okay, but as soon as we get this spectrum, what we're gonna do next? We're gonna look how this excitation energy scales with the system size, and basically the structure would correspond to a conformal tower. So what I plot here is excitation energy obtained with DMRGs, that would be blue dots, for open system with different boundary condition. It's either free or fixed to be a spin up or spin down. And I compare it with a CFT prediction. Well, here I show some expansion that could be looked at different Cheska book. You probably all know this. The CST prediction for different conformal towers. And you see, even for like many excited states, like 30 excited states, we still have reproduced remarkably both the slopes and also the multiplets of the critical states. And we can probe indeed all 3 primary fields that appear in transverse field Ising model. Okay, now with all this knowledge, let's come back to our original spin-on problem, and let's look what we get there. So here I compute first the singlet-triplet gap simply by computing ground state in 2 different sectors, and see that it indeed goes to some finite value in the thermodynamic limit. So the system remains gapped, the magnetic gap doesn't close, but at the same time the system becomes gapless inside the singlet sector. So we have many states that goes down beyond the triplet excitation and scales indeed linearly with 1/L that signals conformal invariance, and moreover it reproduces structure of conformal towers of Ising model, which would be identity here and epsilon here, depending again on the boundary condition. So this basically proves that what we face is indeed a non-magnetic Ising transition, and it complements our previous results on the critical exponent. Now I'm going to move to another interesting point on the phase diagram, this end point, where we move from a continuous transition into first order transition. So as I already mentioned, it happens due to the presence of marginal operator, which changes sign. So here it is negative, and therefore we have some corrections on top of the CFT prediction for this Vezumino in SU2 level 2. Here it is positive, so it normalized to a first order transition, but on the finite size system it still brings some correction. So if I would try to plot my critical exponent in thermodynamic limit, assuming an infinite bond dimension, I would have 3,8 and then drop to 0. But on a finite system, obviously I have something smooth, so I have something big due to log corrections before the endpoint, and then the critical exponent crosses the 3,8 prediction line where the logarithmic correction vanishes, and then it becomes decaying where transition is the first order. So this crossing point gives me an estimate where the critical point is located. And now I probe that it's indeed a true endpoint by looking again at conformal towers. Now it's magnetic, so I compute lowest energy in different magnetic sectors. And I compare it again, I compare my black dots with the CFT predictions that are shown by a line. And I see a remarkable agreement, which means that indeed what I see here is a conformal tower in the absence of log corrections, or with a very small log corrections that I cannot really distinguish here. But now the idea is that due to log correction, due to first order transition, this conformal tower is destroyed as soon as I move away from this endpoint. So here I show an effective slope, an effective velocity of my excited states, different three lowest excited states on both types of boundary conditions. So when conformal tower is restored, they all should be the same. But due to log corrections, due to first order transition, they're different, and therefore conformal tower is destroyed if I try to measure it along critical line away from the endpoint. And that's a nice spider that I see here, and here indeed says that what we observe here is indeed an endpoint. And also one can look at the location, so it's indeed compatible with what we get before. So now, yet another piece of useful information that one can get from DMRG. So we see that here there is a magnetic transition, but also to the same phase we can go through a non-magnetic transition. And the question is, what's the nature, why it is actually so different, what's the difference between these two transitions, and why one of them is magnetic, one of them is not. And we believe that the answer is hidden in the nature of domain wall. So when we try to connect a Haldane phase to a dimerized phase, the domain wall necessarily carries spin 1/2. Well, it is not true for the next nearest neighbor Haldane phase connected to a dimerized phase. And in order to prove it, we actually look again, we go to numerics and look what happens when we try to create this domain wall. So we look at the first order transition here between Haldane phase and dimerized phase, where we expect to have magnetic domain wall. We look at three different quantities. First, local magnetization. Remember observables, it's on-site magnetization. Second is the nearest neighbor correlation. And then is three-side correlation. Basically, it should be large when a system is in Haldane phase, and it should be small when it's in dimerized phase. And I look at three different points. At the first order transition, which is continuation of my Vezumino line, just below it inside Haldane phase, and just above it inside the dimerized phase. And what I see that inside the Haldane phase, I have very pronounced H states, and essentially the Haldane bulk. Large G3, no dimerization. While moving closer to the critical first order transition, my H states start to move to each other. And at the boundary, I have a dimerized domain. And the soliton of a spin 1/2 basically say indeed the domain wall is magnetic. Inside, I have no dimerization and large G3 interactions. It means that my inside domain remains in the Haldane phase. So I have coexistence with the magnetic domain wall. If I move further into a dimerized state, you see I have two domains of different orientation of dimers separated by a delocalized spin 1 excitation, spin 1 spin. Okay, this is the first outlook for this part of the talk. So you see, well, DMRG indeed is a very powerful technique for obviously for gapped system, but also for a critical system. Yes, you have log corrections, but if you combine finite size DMRG, where you still can get sufficiently large bond dimension to converge it well with a boundary conformal field theory, it gives you very powerful technique to characterize the underlying critical theory. And from physical point of view, you see we show there is yet another option for transition to a dimerized state beyond quadrupolar SU3 and magnetic resonance with an SU2 level 2. It's an Ising non-magnetic transition that takes place entirely in an Ising sector. So, are there any questions? Okay, then I move to another one. So this is a completely different story. Yet another extension of DMRG and what one can do with this MPS-based technique. This work has been done in collaboration with Steve White, the inventor of DMRG, you know. And basically it's a tensor network designed to deal with the lattices that has a comp geometry or that can be bring to a comp geometry. So it's a collection of 1D chains coupled to each other through one edge, or one can look at it as a chain highly decorated with such teeth. So it's a natural extension of a DMRG introduced before, or with the fork tensor networks. And this later one is used to study a system of many levels, for example, an atomic system where you have many levels and degrees of freedom could be split into different tensors. Obviously, this is the most simple geometry suitable by comp tensor network, but it's not the only geometry. One can introduce more backbones, and it doesn't really matter where it is situated, so it could be highly decorated ladders, and the computational cost basically scales as a DMRG for the ladder. So as soon as we increase the number of backbone interaction, our cost would scale exponentially with the number of this horizontal interaction, but still, if we keep them sufficiently low, it still remains low. And of course, one can add any type of frustration, like next nearest neighbor interaction along backbone or along twos. And the main goal, of course, is to do something more or less generic, where we have clusters of complicated zero-dimensional objects. So it could be interaction, for example, all-to-all, as soon as system is finite. I mean, one can, in principle, put anything in that here, as soon as we keep an area law satisfy at least along one direction, either along backbone or along the deuce. So, why it is useful? So the goal, from numerical point of view, the goal would be to split two channels of entanglement, one that propagates along the backbone and one that goes along a tooth, into two separate channels, and therefore, if area law is satisfied along at least one direction, we can deal with it with a finite boundary, basically as a DMRG would do. It, for example, implies that inside the clusters, as soon as they are finite, we can bring anything, basically anything that could be computed with DMRG could be brought inside the cluster. Or if we have a gapped state in the cluster, we can in principle make this teeth infinite, as soon as one dimension could be made finite. So this is a numerical setup. So this is a wave function represented as a matrix product state with now a bit of generalization as well in a canonical form. So as before, we have tensors of a rank 3, here shown in blue and pink. And again, we impose normalization. For example, the blue tensors would be right normalized and the pink one would be left normalized. But since we want to keep rank of each tensors at most 3 to keep small computational cost, we split the degrees of freedom of the backbone into two tensors And now these tensors are sitting away from the backbone. It doesn't have physical indices, therefore the rank remains 3. And we have 3 different normalization conditions for this backbone tensors. It either gives an identity matrix when constructed over these 2, or that 2, or these 2 bonds. So it's straightforward generalization of a matrix product state that we have in 1D. Now about matrix product operator. Again, along the twos, inside the twos, it's basically the same MPO that we observe in one-dimensional DMRG, but on the backbone, it has a rank 5 tensor, so it's kind of PEPO, and if we just consider nearest neighbor interaction along all bonds that connect this site, we have such non-zero entries in our matrices. Of course, if you want to include more complicated interaction, you also want to accommodate it in the tensors. And this is how basically the sandwich psi looks like. And now about optimization. So we want to do the same as we've done in DMRG. So we want to optimize iteratively, pair by pair, all tensors of the tensor network. And optimization within the twos is basically the same as optimization of DMRG. You have some, let's say, right part, and all the rest you connect together, you contract, and you get some big fat left part, which however still looks like a left environment in DMRG. So optimization inside the twos looks exactly the same as in DMRG. Now, optimization along the backbone would be a bit different, but there is an idea. So we can treat fully contracted twos as an effective matrix product operator. Instead of physical bond here, we have this auxiliary bond. So it's like fat physical bond in our original DMRG. But if you look at the tensor network now, it looks indeed like a conventional DMRG setup. So we can optimize in a very similar way as DMRG. And what's different is when we try to optimize simultaneously the backbone tensor and a tensor inside the twos, the connect update. And this is not, it cannot be reduced simply to a DMRG because it has 3 environments. But again, playing with the contraction, remember order of contraction matters. You can find the simplest or smallest complexity in which you contract this tensor network and again optimize it in an efficient way. Yeah, come on.
Excuse me.
Yes?
Do you have interactions between different branches?
No.
The random-
No, that's the point. I need to replace the battery. So in principle you can add them, but it would be as bad as DMRG on many like ladders.
I have just a comment that this tensor network can be obtained by removing some sites from the tree tensor network.
Well, it is tree tensor network.
And Vector lattice has been treated by DMRG. So actually, that's how to say, backbone tensor can be treated as it was done in DMRG applied to Vector lattice.
I will show comparison between this competence network and DMRG, but for some reason it doesn't work. Come on. Okay, now I'm connected here, sorry. Before I actually show comparison, let me mention about complexity. So if in the worst case, no, it doesn't work. In the worst case, when all bond dimension is the same in SD, the complexity for backbone update is D5 and it's the worst. For connect update, the complexity is D4. And for inside the twos, it's basically the DMRG, so it's DQ. But for many different problems, for example, if we have more or less a KLT state or near a KLT state on the twos, the complexity is back to a DMRG DQ. Okay, and now the comparison to DMRG. So here what I show is Schmidt values obtained in a comp and in DMRG. Thanks a lot. How to use it? Green one.
Yes, green.
Cool. Thanks. So I look at several different cuts. So one is across a backbone, and obviously it's the same for both setup for DMRG and comp. It's just the same Schmidt value, it's the same decomposition. So red line is the same here and here. It's just different X scale. Now I look at different cut in a comp. So one very close to the backbone, in the middle of the two, on 1/3 and on 2/3 of the tooth. And you see that the Schmidt values decay much faster, and here it's almost zero immediately when I have a comp tensor network. In DMRG instead, my backbone cut actually gives me a fastest decrease of Schmidt values. But when I try to cut across a tooth, I have enormous increase of Schmidt values that decay very slow. So at least for some systems, DMRG is not as effective as a comp tensor network.
Yeah, that's because you have applied that breakup
Of course.
lattices.
Yes,
Yeah.
yes,
What
indeed.
I have said is that DMRG can be applied to beta lattice.
Yes,
And in that case, you have the same cut as you have shown as in the left side.
yes, it's true. Yes. But these cuts, although they are not equivalent exactly, can give us an idea of complexity. And that's my next slide. So indeed, the bond dimension, it's basically, there's no big sense in comparing the bond dimension, but there is a sense in comparing the complexity. And as you can see, for a critical spin 1/2 comp, the complexity of DMRG is comparable to comp tensor network, but it starts to increase a bit higher when we move to a larger comp. And for gapped spin 1 tensor network, comp tensor network, it's actually way higher than what we observe with comp tensor network. So I agree that the bond dimension itself doesn't really bring much information because it's different by partition. But the complexity actually quite straightforward.
What are you what is you comparing? Are you comparing DMRG means that zigzag break,
Yes.
and comp means that so you haven't checked that. Okay. This is a minor point, so let us discuss it later.
Yes, well, but no, I mean, this is a complexity you can indeed compare.
You compare the accuracy?
Hmm?
Or you compare the accuracy?
I fix the accuracy and compare the complexity. Yeah, one can do other way around, of course. Okay. Let's come with some examples. And first example is a spin 1 comb lattice. So I have a spin 1 tooth coupled through a backbone only along one line, and I want to and I tune this backbone interaction. So first of all, the system has a gapped edges. We know it's in the Halden phase. And for now, let me just remove some edge states from the tip of the tooth. So I really probe what happens here on the backbone. So I replace my spin 1 by spin 1/2 here. And I look what happens here when I tune backbone interaction. And what I expect is the edge state that appears in the Halden phase would form a critical chain as soon as my interaction is non-zero. And in principle, that's indeed what I see by looking again at the Friedel oscillation along the backbone and at the central charge by scaling of entanglement entropy. I see central charge close to 1, which would be for critical spin 1/2 chain, and critical exponent close to 1/2. The discrepancy is due to log corrections that are present in this particular point. But you see the finite size dependence is very small along the tooth. So it's a gap tooth. So it doesn't really matter whether I include 10 or 20 sites. The finite size effect is much smaller. But now let's look at the correlations, and here I show an entire comb, 20 by 20, and I show nearest neighbor correlations computed on this lattice. And what you can immediately notice that most of them, since I don't have interaction between these sides, are located within the tooth. But along the backbone, I have some indeed important interactions. Let's look closer. So when my backbone interaction is small, I indeed see strong correlations on the tooth and a weaker correlation that would rather correspond to a critical chain that I expected to see on a backbone. But if I increase a backbone interaction, what I actually see is that correlation here becomes much larger than correlation between the first two sides on the tooth. And it means that this picture is no longer void, but rather I form a Halden chain here, and my critical chain jumps one step above. Now let me restore this spin 1/2 edge at the tips of the tooth and look what happens. And why it is interesting, because remember, if I have even number of particles on a Halden chain, my edge states form a singlet in the ground state. But if I have odd number of particles, they form a triplet. And if I have a triplet, I have effective spin 1. It's very weird, spin 1, very much delocalized over a tooth, but still I can form a Halden chain of the spin 1 as soon as I turn on the interaction along the backbone. And if I form a Halden state, I can expect some edge states. And that's indeed what I see. So I take a comb where backbone interaction is equal to tooth interaction, and I look in the sector of total magnetization 1, and what I observe is a localized edge state. Well, it's kind of higher order edge states, but it's still one-dimensional lattice. So indeed you see this higher order edge states localized on the entire cluster. Now let's move to another model, which is in some cases simpler because it's spin 1/2, but in some cases it's more complicated because it's a critical tooth now. And let's look what would happen when I try to tune the interaction, the backbone interaction between these critical teeth. So when backbone interaction is very weak, I basically have decoupled critical chain with L sides each. And my magnetization looks, well, as it would be in the critical chain. I have all chains equivalent, so this would be a backbone, and that would be my teeth. When I have increased the backbone interaction, when it is comparable to the tooth interaction, effectively I can look at the comb as a collection of longer chains. So it's, well, it's not exactly, but it's almost like a 2L chains, either this side or this one. And then magnetization envelope indeed looks more or less as it would be for this type of chain. But then when I increase the backbone interaction even further, what happens, I actually decouple this backbone from the rest of the tensor network, similar to what happens in spin 1. So now I have critical chain on the backbone, but my critical teeth actually one side shorter, so they are only of L-1 sides. And I see it different, I'm not sure whether you can distinguish, but it's butterfly structure of the magnetization profile on this part.
Excuse me,
Yes.
I have a question. If you change the system size along the tooth, I mean that the length, when I'm, how can I say that, result changes when the length of tooth is even or more?
Yes, it is. Yes, I'll come to it.
Oh, thank you.
Of course, yes. So let's now also look at the nearest neighbor correlation, similar as before, and as entanglement. So this would be nearest neighbor correlation and entanglement. When backbone interaction is small, all my correlation are within the tooth, And you know, it's basically it's critical spin 1/2 chain. So due to open boundary, we see some Friedel oscillation. We see some dimerization close to the edges. It decreases algebraically towards the center. And the same with entanglement. Entanglement is also enclosed, completely contained within the tooth. But now, when I start to tune a backbone interaction, what happens is basically isotropic correlation between nearest neighbors and huge increase of entanglement, which means the system is highly critical, if I can say so. And if I continue to increase backbone interaction, you see this decoupling. So now, again, I indeed decouple my first side, my backbone, from the rest of the system, and this more dimerized boundary now favor between the second and the third side. And the same is true for entanglement. You see a highly entangled critical backbone, and then the entanglement is contained inside the tooth. So now I try to look at the excitations, and here what I plot is a magnetization profile on the comb in the sector with total magnetization 1 for different value of backbone interaction up to 1, so I don't go too far. And when backbone interaction is very small, I see a kind of soliton structure along the backbone direction and a butterfly structure as we would expect for a single chain. If I now compute it also for a higher magnetization in SD total 2 and 3, what I see is that the slope actually increases. Well, the slope is given by 1, 2, and 3. It's not like I would have if I would accommodate all these magnons inside a critical chain. Then, according to Wesermann-Witten theory, I would have a slope 1, 4, and 9 squared by squared. But instead, I have a slope that increases by 1 every time. It means that I have a solitonic structure and excite my teeth separately. So when I have magnetization, total magnetization 1, I excite my one teeth. When I have total magnetization 2, I excite 2 separate teeth that hardly talk to each other. For magnetization 3, I excite 3 separate teeth, each to magnetization 1. And the solitonic structure preserved, you can see it very well, they agree pretty much with the slope. So indeed, it's a very small correction there. And you see it's also in the profile along this direction. But now, when I increase the bone dimension slightly, I start to deform my butterfly structure along the tooth. So it's no longer like L sides spin and chain, but it's a bit different, and I more or less delocalized along the backbone. It's even more pronounced here in this situation when backbone interaction is actually equal to a tooth interaction. So what happens, again, try to think about it as an open folded comb. So we have a butterfly structure similar as before, but now on 2L sides. And it's completely delocalized along the backbone. But what's interesting that in this particular case, it doesn't really, the spectrum, it doesn't scale linearly, neither with the number of sides, nor with any of linear dimension. And it doesn't really depend whether I have even or odd number of sides. So it's kind of weird spectrum, similar as we saw yesterday in Sierpinski carpet. But Sierpinski carpet has a fractional dimension. Here we have dimension 1. We don't know which direction of this one, but it's one-dimensional system. But we still cannot entirely describe it by a one-dimensional CFT. And in order to understand what happened there, let me step back and look at a simple situation. So this would be an excitation with odd number of sides per teeth. So here, as soon as I have odd number of sides, my ground state on the teeth is spin 1/2. So effectively, I have a spin 1/2 chain where this 1/2 degrees of freedom is delocalized along the teeth since it's critical. And therefore, I look at this spectrum, excitation spectrum, which now indeed has the same structure as this critical spin 1/2 chain. So my slope is 1, 4, 9, as it would be for Wesermann-Witten chain. But it scales not with the number of tooths, neither with the number of sides per tooth. It scales with the total length of a chain. And again, it's clear because what should actually enter here is the distance between the two, the entire length of a critical chain. So it's actually natural to expect to have an entire product of two dimensions in here, and not just length of backbone. But then it actually helps us to understand what's going on in this particular picture. So what happens is, again, we have a delocalized spin degrees of freedom, but it's not completely delocalized. It's somehow favored to be far from a backbone, but not yet localized at the tips. So we have some intermediate situation, and therefore it's intermediate and it's not universal. So it cannot be really described by CFT. Or it can be described by CFT at this particular point if we figure out the effective length. And I move to my last example of the comp, which is still a work in progress. So this is a transverse field Ising comp. As before, we have critical T's, and we tune X-axis interaction on the backbone and look what's going on there. So what I show here is on-site magnetization for different values of a backbone interaction. And you see, when my backbone interaction is small enough, I have polarized H states for all critical T's, as I would have for separate chains. But then as soon as I try to tune backbone interaction to a bit higher value, I don't want to have a polarized backbone anymore. I want to have I want to form them nearest neighbor correlations. And I suppress my polarization here, but what I rest with is very weird H states. Again, it's a kind of higher order H states that only located here at the corner and suppressed along the backbone. And if I look at the order parameter, here is polarization as a function of backbone, I see very smooth change in the polarization, which however becomes more and more sharper, and you see a normal finite size effect. And by looking at the derivative of this polarization, we actually see the dip, we see a pronounced minimum. So something indeed happens there, but it's not clear whether it's a crossover or it's kind of transition. And if you look at the SX polarization along another direction, again what we see is very pronounced first order transition on a finite size chain. But it really looks like in the thermodynamic linear we're going to have a continuous transition there. And one of the reasons why it actually can happen is because in our finite size cluster, due to open boundary condition, we induce a non-uniform field, and the way to overcome this, a non-uniform transverse field, longitudinal field, means that I'm no longer, I lift my degeneracy that would appear in a critical Ising and bring it into first order. And to restore this degeneracy, I need to make an isotropic and uniform field, and one of the ways of doing it is to consider this sunny model of with periodic boundary conditions. So again, it's going to be a cone with a backbone, and it is sticking out of it. And with this, I basically would like to thank you for your attention and let you read the outlook.
You have calculated the age excitation distribution on the cone. Yeah. And you have shown that it prefers to be localized around the boundary.
Here or no?
In one case.
Mhm.
The previous.
This one.
Okay, it is okay. And my question is whether the interaction is totally uniform along cone or not.
Yes.
Okay. So in ancient ages, in order to obtain Haldane gap on in one chain by using exact diagonalization or DMRG, they weakened the last bond. Do you know that? They put a weaker Heisenberg coupling at the both edges of the one-dimensional chain. Yeah, and they did it because it drastically reduced the finite size effect. Yeah, the reason is that it kills the kinetic energy of the excited
Yes,
locality.
makes sense, yes.
So what will happen if you include the last one at each cone? I suppose the
Yeah, I suppose it's going to be more localized here,
yeah,
right? Yeah, I suppose so.
do you believe? Yeah, do you believe?
Yes.
Okay. Then it's okay.
Yeah.
So in young like cone structure tensor, the backbones look like an MPS and the branches are still like an MPS ones. So is it possible to combine some other types of tensors like tree tensors or even
Yes, that's the point. It's very flexible algorithm. Yeah. So, I mean, here I consider the most simple case where all twos are equal, and but yeah, you can play. It's that's the whole beauty of matrix product state. You can modify anything locally.
Yeah, regarding to this point. Okay. This network, common network, yeah, you can set up a canonical form on this type of network. That's why you can apply the DMRG scheme easily.
Yes.
Is it right?
Yes, there are no loops, and
Yeah.
therefore, yes.
So when there is no loops, it is possible to apply the DMRG like algorithm. Okay, probably the terminologies makes confusion. Probably you use DMRG
Yes.
just for one-dimensional chain, no?
Let's say the optimization is indeed very similar to DMRG, but the tensor networks are connected in a comb-like geometry.
Comb-like?
In a geometry that repeats comb.
Yeah. So, but that tensor network is canonical.
Yes.
As long as the tensor network is canonical, just by sandwiching that tensor network to Hamiltonian, you can divide it into environment tensor
Yes.
and effective Hamiltonian.
Exactly, that's what we're doing. Yeah.
So this is actually DMRG itself.
Yes.
Yeah,
Yes.
and what I would like to point it out is that previously they applied, do you know that previously they applied DMRG on beta lattice?
Yes.
Yeah. So in that case, they assumed canonical form for the tensor network. So for the beta lattice system, they construct the ground state or trial state, variational state, as a combination of canonical tensors.
That's what we are doing here.
Yeah.
Also. Yes.
So that is the same.
Yeah, the geometry is different, but the idea is the same. Yes.
Yeah, the idea itself is the same,
Yes.
and algorithm itself is the same, and just by removing several branches from that beta lattice, you obtain complete network.
Well, yes, but you have to remove a lot of them. No?
Yeah.
Yes.
So just by removing many branches from the beta lattice, you reach this network.
Yes, but in principle, it's just different tree tensor network. You can
Yeah.
construct any other tree tensor network and optimize it in a way which would be the most efficient for this particular tree.
Yeah.
Yes.
So from the algorithmic viewpoint, they share the many points in common. So DMRG, what was applied to data lattice, has many aspects in common with your current approach. From the
Yes, I suppose so, as for any three-tensor network, yes.
That is the point I said in the question.
Yes.
So now we share the same opinion. Thank you. I have a question for the first topics. If my memory is correct, in the ground state phase diagram, there the Harding phase includes the incommensurate.
Yes. I don't
So I'm
know.
wondering that the accuracy, actually the phase boundary between the dimerized phase and the Harding phase is
Oh, between here.
around such kinds, around the how can I say, the crossing point.
Around triple point.
Yes, near the triple point, the ground state is incommensurate.
Yes, indeed. Well, ground state is actually incommensurate all the way around here.
Yeah.
Yeah.
Accuracy, so I'm wondering that that is easy to obtain the high accuracy by using the DMRG. To this
well,
the end
this-
point of the second order transition, or how can I say, the order of the phase criticality, phase transition between these three phases.
Surprisingly, the most problems due to incommensurability was here. Here, since exact line hits the first order transition, the correlation length is actually very small, so it's not a problem there. And here, I don't know, it's probably coincidence, but we don't feel really incommensurability as soon as our system size is larger than 100 sites.
And I have another question. Could you find the presence of the spin at the phase boundary between Harding and dimerized?
Here.
Or,
Oh, here. Yes, here.
yeah, which one is okay?
Both. Both.
I have a question, concerning with this phase diagram. The continuous phase transition line between Hordern phase and the dimerized phase, you say on the whole line, the central charge is 3
Yes.
I wonder whether there are any speciality at this ending point
No, the
compared
central.
with the other point on the line,
No, that's the point. No, central charge remains the same. Critical
No.
exponent remains.
except the central charge. Are you found any differences between the ending point and the other point on the line?
Well, log corrections, logarithmic corrections.
Are different, yeah?
Well, they vanish at this point, and they're present along the line. So if you try,
What kind of log correction for what? For which quantity?
For many quantities, for example, for apparent critical exponent, so critical exponent that we try to measure along this line with finite size system is larger than CFT prediction. Central charge is, if I remember, smaller.
I see.
It was computed before me, so the energy spectrum is different. So if you try to plot a conformal tower, they don't have the same integer scaling, but they inclines away from this integer slope. So indeed we see a difference,
I see.
but we expect them.
Are there any renormalization flows around this line? This critical line?
Yes, I think so, yes. Indeed, it goes from here to...
No. On the continuum transition line.
Oh, it goes up to C equal to 3 half.
Yes,
So it's exactly like the spin-off chain, except the spin-off chain is no relevant operator. So
exactly, yeah.
that line is sort of like this J1, J2 spin-off chain. And that point is like the transition in the spin-off chain. Right?
Yes,
Isn't
you're
it?
right, yes. Yes, so in many senses, it's kind of generalization of KT transition. Well, it's a special point on the...
Yeah. There's just one fixed point.
Yes. Yes. But if you look at J1, J2 spin 1/2, it's one fixed KT transition.
I think usually when people talk about KT, they think of this line of fixed points. But here there's just one fixed point.
Yes.
So you flow up to that point and you go.
Mhm.
Is it possible that this other transition can be continuous, the one from the handling to the...
Yes.
It's possible it's
Yes, it
another
is.
point? Or is there theory for that?
Let's say we expect it to become continuous at some point, but it's extremely difficult to prove.
And so what...
Certainly, we can have a phase transition from Holland phase into another kind of dimerized phase, just along the horizontal, And in that case, the critical theory is described by spin. The central charge equal to 1 CFT instead of 3 half.
Yeah, but that would be compatible to what you asked, right?
Yeah, so I guess I was asking about the Halley to the...
Yeah, here.
Yeah, so that thing you said can also be continuous.
That would be natural to expect, as I said. So if we have boson plus Ising here, it's natural to expect that if we have Ising separately here, at some point we might have boson separately. But yeah, it's very difficult. Again, because it's incommensurate.
So sorry, I didn't understand the comment about incommensuration. Are you saying this phase diagram is not complete? There's some other regions where this diagonalization becomes...
No, this is a long-range phase diagram. On top of it, we also computed short-range phase diagram. That, for example, this Halden phase is enriched with many different short-range orders. So long-range order remains the same, but there are like 5 or 6 short-range phases inside there, and also next nearest neighbor Halden phase is short-range incommensurate. Which means that if you try to compute like spin-spin correlation, they do not decay simply exponentially, but on top of exponential decay, you have some cosine with incommensurate wave vector.
And does that first order line, does it become, when it touches the continuous line, does it become weaker or something like that? Or is it...
Here,
Yeah.
not really, because it doesn't touch it. You see, Ising really like cross it. But there is yet another subtlety on this. So it's since it's marginal operators that drives this transition to a first order, the gap opens exponentially slow. Therefore, it's on a finite size system. It looks like a continuous transition for a while. But around this point, no, it's finite correlation length. I mean, obviously it's infinite close to here, but it's not weak first order.
But I mean, on the black line, the solid black line, the dimerization should go to 0 continuously.
Yes.
So then you might think that the transition between Halley and dimerized by continuity also should be, I mean, that first order line should somehow become weaker and reduce to that point.
Well, yeah, indeed, correlation length increases, but still you can handle it. I mean, we didn't try to really compute it like this. It would be too difficult, right? So we tried to locate this line with a cut, which would be more suitable. And also we tried to locate this solid line with a cut like this, right? So we...
Okay. It's time to speak again.